every single grade. And that's the story of the evolution of Wade.
BC students, as we continue chapter 6, we move on to 6-3, and boy, is this section just crammed full of real life problems that I've researched myself, of course. A good calculus teacher will show you all these real life applications, all right? And a not so good one will just kind of plow through the book or just do boring examples. So, real life, all right? Did a little chemistry research, and I thought about this thing that if you've taken chemistry, you've probably learned about it. It's called the differential rate law, okay? And so in chemistry, you probably used the differential rate law or will use it this year if you're currently in chemistry, but you're never shown why the differential rate law even works. So this is the calculus behind the chemistry, all right? So we've got H2O2, so that's hydrogen peroxide. Some of you probably have that in your house. If your parents have one of those little brown bottles and inside you got the hydrogen peroxide, you get a cut, you pour it all over the cut to try to disinfect it, okay? So we've got some of this stuff sitting around, and after 15 years, it should be about 4% of its original concentration, unless you left it out in the sunlight, which would make it decay a lot faster, of course. You see the negative right here is telling us the decay, something's going away and not increasing. All right, you see the d and the dt, it's a derivative, okay? So we're going to try to solve this real life differential equation. That's exactly what this is. Okay, so T is years, H2O2 is concentration. First thing I would do, at least in a calculus class, you can't do this in chemistry, you can do this in calculus. Let's replace H2O2 with just Y, or whatever letter you want, okay? Or you can make it capital H or whatever. So the T is always like the X in math classes, even back in integrated 3. T is like X, and then this would obviously be like your Y. So let's write this rate law as negative dy over dt equals k times y. All right, that'll make it a little bit more practical, more manageable. I don't want to keep writing H2O2 and the square brackets over and over and over and over again, right? Okay, just for fun, I gave you this little equation right here from chemistry. Eventually, when hydrogen peroxide decays and it becomes less and less and less strong and less potent over the years, it turns into H2O, which you all know is water, and O2, which is oxygen. How about that? Just water and oxygen. And then it's no longer hydrogen peroxide that you originally bought at the store. So, how do I solve this differential equation? Well, since we're on the derivative and we're trying to get back to the original function, the name of the game in this chapter is integrate both sides and use separation of variables, all right? Just like the problems the other day with the city that was in India and examples like that, right? Just like the other day when we had the city in India that was increasing so quickly, its population, right? Or the radioactivity problem, the half-life, lots of science, real-life applications. So I'm going to multiply the dt up to the other side because every side must have a d something to accommodate the integral. I'm going to divide the y from both sides and basically divide it under the other one because we have to get all the y's together on one side. So you're going to get the integral of negative dy over y, but hold on. Mr. Wade likes his dy's on the side, and I'd rather you write this. Negative 1 over y dy, if that makes sense, okay? So the y divides underneath. Push that off to the side. Over here you get the integral of k times dt. All right, now we've got integrals and d's on both sides. We've got all the y's with the y's. That's great. Okay, integration of negative 1 over y. Wouldn't the negative just carry? And you would get the natural log of the absolute value of y, right? Definitely a natural log problem. And yet again, so many natural log applications in real life. I told you about a lot of those in integrated 3. I couldn't tell you about any of this stuff in integrated 3 because you didn't understand integration yet, right? But look at this, okay? Real life logs. Integration of k, considering that t is the variable, right? The integration of k is normally kx, but this time it's kt, just like before. all right? And then one side gets a plus c. It doesn't matter what side you put it on, but if you put it away from the y, that always saves you a step later, saves you one step. Might as well do it. And now we've done this before with the radioactivity problem. There's a K and a C. You've got to find C and you've got to find K. So you need 2 hints to find the 2 unknowns. All right, you start with your initial value. At time 0, what was happening, right? Then you go to what's called your secondary value. At time, what, 15 years down the road? At time equals 15, something was happening. Okay. Now, normally, like in the radioactivity problem, I gave you at time 0, you had 100 rads of radioactinium, right? This is the first time I have not given you an original amount. What is this, a 16-ounce bottle, an 8-ounce bottle, a 12-ounce bottle? Like, how much do we have, right? And how much actual hydrogen peroxide is in there, all right? We don't know, do we? We do know one thing. When we bought it, it was 100% concentration, all right? That's the only thing we know. So the Y, the amount, the how much, is going to equal 100% of, we don't know. Why don't we call it this? Let's call it capital H. That's kind of why I did Y instead of H over here. Let's call it capital H for 100% of hydrogen peroxide. There's a secret 1 in front of that H that stands for 100%, okay? I had all of it. So this is really weird because this has never happened before to us, that you don't even know how much you started with. And believe it or not, you can still solve the equation if you just follow the rules that I've set for you. After 15 years, Y equals how much was there? 99% of the time I give you how much you started with and then how much you have later. This is the one exception. I didn't tell you how much you had later, but I did tell you that it was 4% of what you started with. Okay, that's all we need. 4% of the original amount H would be 0.04 of H, or times H. Does that make sense? So you had one whole, some kind of amount, and you have 4% of that, some kind of amount, okay? That's all you can do. All right, so in this one question, you won't have numbers yet. We will get there. All right, we're going to find the real-life K value that actually applies to real-life hydrogen peroxide. Okay, let's try this. Don't we always plug in the initial value first to find the C, and then you plug in the secondary value to find the K? That's always the case. All right? Some of these differential equations have C and K. Some of them just have a C. It depends. So let's do negative natural log of absolute value of H goes for Y, capital H, equals K, T becomes 0, plus C. That's the brilliance of actually using the initial value. The initial value always happens at time 0, and time 0 will always hide your K's, and you can find C. Although every time we've done this in this chapter, we've gotten C equals an actual number. Now we got C equals negative natural log of absolute value of capital H, whatever that is. Don't worry, it'll work. Okay, now, what do you do when you find something in calculus? You plug it back in and you start to use it to your advantage. We just found C. We're going to put it back into the equation for C. Let's try this board over here because I'm already out of room. So we'll put negative natural log of absolute value of Y equals KT plus C gets replaced with minus natural log of absolute value of H. Okay, now we're getting somewhere. If we could just find the K value, and we're hoping this comes out to be a number and not a letter, right? What do we have? Y's, K's, T's, and H's. We got so many letters, and I guess if you count L and N, you got more letters. Alphabet soup. That's all right. We can fix it. Secondary value. Negative natural log of absolute value of Y gets replaced with 4% of the original, whatever that was, equals K times T was 15 minus natural log of absolute value of H.
So you plug in the t value and the y value, and you've got several h's, but don't worry. Okay, get k by itself. K times 15 is positive. It's 15k, right? If the unknown thing you're trying to solve for is positive, leave it alone. Isn't that our theory in this class, right? Kind of our theme. If the thing you're trying to solve for is negative, move it. Leave it alone. Add this one to the other side. Okay? Matter of fact, I'll even put it in front because it's nice and positive. I don't like to lead off with a negative if I can avoid it. So let's add this to the other side. Natural log absolute value of h minus natural log of absolute value of 4% of h equals 15k. You are almost at the end. You've almost solved this problem right here. You learned something in integrated 3 and pre-calculus that comes in so handy right now. Subtraction of logs makes division. One of the themes, one of the sub-themes in this chapter for sure, bringing that back. Natural log, both inside an absolute value of h divided by 4% of h. Okay, using those old properties from your former math classes. All right, and finally it happens. The h's cancel. There they go. And you get the natural log of the absolute value. Don't make the silly mistake that a lot of calculus students make. A lot of calculus students write 0.04. Oh, give your calculus teacher a heart attack. The 0.0, it's not 0.04. The 0.04 is on the bottom. It's 1 over 0.04, right? Don't you float that to the top. Leave that on the bottom. Okay, now we've got to do a little bit of integrated 3 pre-calculus trickery to get this to work. You've done the calculus. Okay? Matter of fact, you did the calculus when you integrated the whole thing. Everything else is just review, but stuff you've never seen before. Okay, what do we do next? Well, you certainly can't have a decimal and a fraction, can you? Let's think about what that is. Isn't 4% 4 out of 100? And even better, doesn't that reduce to be 1/25th? So think about this. That is 1 divided by 1/25th. Okay? Try to get to fraction world. Decimals are just the death of you in calculus. Try to get to fractions, all right? They're so much easier to manage. And that's how they do this on the AP test. So the natural log of the absolute value of 1 over 1/25th, well, 1 over anything is its reciprocal. That's a mathematical fact. 1 over 1/25th is simply 25 over 1. You can do a keep, change, flip, or you can just remember that 1 over anything is a reciprocal. All right? And then, of course, you can drop the 1. That's silly. And also, the absolute value of a positive is a positive, so stays the same. 15k equals natural log of, drop the bars, 25. And if you divide both sides by 15, k equals natural log of 25 over 15. Okay? That's not a bad answer. I'd probably take that. It's not the perfect answer. You're not really supposed to leave a perfect square inside of a natural log or a perfect cube or a perfect quartic or any of those. So it's better to make 25 into 5 squared, as you'll actually see in this chapter. And then aren't you supposed to kick your powers out to the front? So the 2 kicks out to the front, and you get 2/15ths. And I'm going to write the natural log of 5 on the side, although you could put it on the top. Kind of looks better like that. Okay? 2/15ths natural log 5. So if you leave it 25, I probably wouldn't take off any points on a test. But if you're trying to match a multiple choice on the AP test, they're going to break it down because they always do the proper thing. That, my friends, is the real-life K constant of hydrogen peroxide. Whatever that is a decimal. Interesting, right? Okay, let's try another one, letter B, where we've got a bathtub. And the water is filled up to 16 inches. You pull the plug, and the water starts to drain. And it satisfies the differential equation dH dt equals K squared of H. Now, what is dH dt? It's the change in the height with respect to time. That's how you interpret or read dH dt. Change in height with respect to time. Wouldn't that be H is inches, T is minutes,
The derivative is telling you inches per minute, what the rate is, okay? Now, of course, a lot of things in the real world are just very steady, you know? I'm gonna drain something and it's just gonna leak out at 2 cubic centimeters per minute, okay? Very constant. But a lot of differential equations are with respect to another variable. It's gonna change over time. It's gonna drain the bathtub in a square root fashion. So quickly, and then it's gonna kind of slow down, all right? Maybe it's got some kind of clog or something, all right? Quick draining and then level off. Okay, so that's inches per minute. Let's try to solve the differential equation. All right, let's try it. Well, step 1, integrate both sides. Classic separation of variables. So let's keep the dh where that is. But we're going to multiply the dt up and divide the square root of h back down. So the square root of h is going to come down underneath this one. And then integration of k. And the dt is going to multiply up to it. All right. Differential equations made easy with Mr. Wade. All right, before you integrate something, don't you have to rewrite it in proper form? And I don't like that h in the denominator. I don't like the fact that it has a radical either. So isn't that h to the 1/2? But we could bump it up and call it h to the negative 1/2. Okay, now your integration ready. And you got your h's with your h's, right? So the integration of anything to a power would be add 1 to the power. Negative 1/2 plus 1 is positive 1/2. Divided by the new power, positive 1/2. The integration of k is k times t again. Pick a side for the plus c. Because h is in the top right corner, that's the one we're trying to solve for. H is like my y. So put the plus c away from the thing you're trying to solve for, always, okay? And then dividing by 1/2, take the reciprocal. That's like multiplying by 2. So keep, change, flip that thing. All right, we need hints. We're going to, again, find c and k. All right, let's go to the initial. Let's put it up here. Initial value at time 0. The bathtub was filled to 16 inches deep. H equals 16. At time something later. Oh, hint. In the first minute, it's already drained down to 9 inches. It's draining pretty quickly, actually. So when t equals 1 minute, the height of the water is now 9. Okay? Those are your 2 hints right there. All right. Plug in the initial value first. So 2, let's change h to the 1/2 into square root of h, right? 2 square root of h, we're going to plug in 16. Ooh, nice choice, Mr. Wade. Perfect square inches, very good. 2 square root of 16 equals k times t, which is 0, plus c. If you feel like we're just doing basic algebra right now, we are. It's calculus, and then it's pretty much integrated 1, integrated 2, honestly, even middle school math, okay? That's really what you're doing. Square root of 16 is 4. 4 times 2 is 8. That cancels out the k, hides the k temporarily. C. The c value is 8 for this particular bathtub, all right? What do you do when you find something? You plug it back in. You use it to your advantage, right? So the new equation is 2 square root of h equals k times t plus no longer c. We now know that that's plus 8. Okay, we're making progress. All right, now, secondary value. After 1 minute, we're down to 9 inches as the water level drops. Let's plug those 2 in and find the k value. All right, we're out of room already. Let's go to the second board. So 2 square root of h. Now we're going to plug in 9 for h equals k times t, which is 1, plus 8. This should give us the k value. It's the only variable left, okay? Although really it's a constant, but it's the only letter left. Nice choice, Mr. Wade. Square root of 9, thank you. That's 3 times 2 is 6 equals k plus 8. The k equals -2, 1 step closer, all right? Wonder why k turned out to be negative. Oh yeah, it's the rate constant. K is known as the rate constant. We've said that several times. The bathtub is draining. If you're filling something,
your K is going to be positive. Real life, it makes sense, right? Okay, what do you do when you find something? Plug it back in. 2 squared of h equals K times T becomes negative 2 times T plus 8. We have almost solved the differential equation. Now, normally if I said solve it, you would get h by itself, but hold on, we've got a new twist. We don't want to solve it this time. We simply want to find how long it's going to take to drain the whole bathtub. Could you get h by itself? You could. You don't have to. When will we know that the bathtub is fully drained? When the height of the water gets to 0. I bet some of you were thinking that out there too. Precisely. So it's fully drained when h is 0. Turns out we're actually trying to find out how long it takes. If you're answering a how long question, aren't you actually trying to solve for t, not h? You're trying to find time. So there's no need to scramble this and get h by itself because then you just have to undo everything and get t by itself. All right, so fully drained, put in 0, 2 times square root of 0 is 0, and then you suddenly realize, oh, I'm just getting t by itself. This really is middle school math. And I don't like my t's to be negative, do I? Mr. Wade likes his 2 t's to be positive. Add it over. Do not subtract that 8. You're better than that. Add 2t to the other side. 2t equals 8. T equals 4. What is t in? Hours, minutes, seconds, weeks? Minutes. Final answer, at this rate, it'll take us exactly 4 minutes to drain the whole bathtub. Real life math, what can I tell you? All right, letter C. And I've said it before and I'll say it again. Mr. Wade can link anything to food because I love food. You know those Sister Schubert rolls that come frozen and they're the little sausage wraps? All gone. That's the good stuff right there. This is the differential equation, after experimenting with a few rolls at home myself, that models how quickly it warms up in the oven. All right? It's going to heat dramatically from frozen, and then it's going to kind of level off because eventually it's going to kind of gravitate towards the internal temperature of the oven. Makes sense? All right. So at time equals 0, I'll go ahead and give you this. At time 0, the temperature of the rolls is 0 degrees Celsius. Mr. Wade, why Celsius instead of Fahrenheit? Because every country in the world uses Celsius, right? Except for us stubborn Americans. The Bahamas uses Fahrenheit. Belize, which is down in Central America. And Palau, which is a tiny country in the middle of the Pacific Ocean, a little island, all right? Other than those 4 nations, everybody else uses Celsius. So we'll go with Celsius, all right? It's a very scientific thing. All right, now if any of you out there are researching or Googling, yes, the standard American refrigerator and freezer have certain temperatures. The typical American freezer is at negative 18 Celsius, okay? And this is actually 0 Celsius. So maybe they've been outside the freezer for a little bit and they've warmed up a little bit, okay? That's fine. All right, so time 0, Celsius 0. There's only one difference between this one and all the other differential equations I've shown you. So far, I've always put dy dx by itself. dh dt, we just did dh dt, I had it by itself, right? We've done dr dt for radioactivity. The dy dx kind of thing was by itself. For the first time ever, the dy dx type of derivative is not alone. See this? It's d capital T for temperature over d lowercase t for time, which would be degrees Celsius per minute that it's changing as it warms up, right? Capital T, lowercase t, Celsius degrees per minute, okay? This is all very closely related to real life, of course. So what should you do first? If the dy dx is always by itself and it's not here, but you want to make this look like the other problems, wouldn't you get the dy dx kind of thing by itself first so that everything else is normal? Okay, we do have a decimal. We'll have to deal with that. It's not too bad though. So, get the dt over dt by itself, subtract this thing away from it. So 4 minus 0.02 capital T is equal to 2 dt over dt. D capital T over d lowercase t, all right? Time and temperature. Gets a little crazy. All right, one more thing. To get d capital T over dt, get rid of that 2. Divide both sides by 2. Okay? And since 2 goes into 4 and 2 goes into 0.02, go ahead and divide it into both. It'll make this problem easier for you. So, but what you can't do, don't do 4 over 2 is just 2 and ignore the other one. You can never do that. But you can share it. If you share it with everybody, it's fine. 4 divided by 2 is 2, minus half of 0.02 is 0.01, capital T. So you can do that. Equals d capital T over d lowercase t. All right. Now you've isolated your dy dx looking thing. Now you can do business as usual. All right? And in this chapter, business as usual is separation of variables. We are going to integrate the derivative so we can get back to the original function. Let me put this in parentheses. But this integral needs a d something. And you've got too many d somethings over here. Multiply the dt up to the other side. Let's do that first, just that one step. 2 minus 0.01 capital T d lowercase t equals the integral of d capital T. So I just multiplied the little dt up. All right. Do you see a problem, though, that has not happened yet in this chapter? Oh, man, I got capital T's and lowercase t's on the same side. Aren't we supposed to get all the lowercase t's on one side and the capital T's on the other side away from each other? It's like cheetahs and gazelles. They don't belong in the same cage at the zoo. All right. We need to take this whole parentheses and get it over there. You are not allowed to detach this 0.01 capital T because it's subtraction or addition. You can't detach it and throw it over here. That doesn't work, not when you have a dt multiplied to it. So now, there's only one way. The opposite of multiplication is division. You have to divide by that whole piece and keep it together, all right? Divide both sides by 2 minus 0.01 capital T. It's the only way. It'll cancel out over here, and now you'll just get the integration of dt equals the integration of, I like my d capital T on the side, 1 over 2 minus 0.01 capital T d capital T on the side. Okay? First time we've seen this kind of thing in this chapter, where you had to divide by an entire piece. Because I see calculus students trying to add this over. You can't add it over when the dt is like shared with it, okay? And you can't distribute the dt. That doesn't help either. All right, now that you finally got to a good place here with some algebraic maneuvers, basically, the integration of essentially 1 dt isn't the integration of 1x, but d lowercase t tells you that it's t, okay? Lowercase t. Leave a little space right there, just for a second. Over here, is that t to the first on the bottom? And is it also technically quantity to the first? Wait a minute. Isn't that classic natural log, right? T to the first and quantity to the first on the bottom. It's natural log of the absolute value of 2 minus 0.01 capital T, close your absolute value. Do not forget to divide by the chain rule, because if you don't do U substitution, you must divide by the chain. It's one or the other, okay? The chain rule of the base, 2, derivative is 0. The rest of it, the derivative is simply negative 0.01. Drop the t, okay? Because the derivative of constant x is just constant, same thing here. Now we're cooking, but you got to put a plus c on one side or the other. Who is in the top right corner? Okay, or even right here. Capital T was in the top right corner. That's like your y. You want to solve for capital T. So don't put more plus c's on it. Put plus c's away from the capital T. Put it on the lowercase t pretty much every time. All right? And I do not like a decimal in a fraction. I don't even like the negative on the bottom either. Isn't negative 0.01 the same as negative 1 out of 100? Keep, change, flip. All right? T plus C equals, flip that over, negative 100 natural log of the absolute value of 2 minus 0.01 capital T, close the absolute value. So far, so good. So let's put it over here on this board so we can finish it off. We're basically doing middle school math, all right? Just a little bit of calculus. So we know in the beginning, the initial value. At time 0, the temperature was 0 degrees Celsius. So when lowercase t equals 0, it turns out that capital T equals 0, okay? And so if you drop the 0, the C value is negative 100 natural log of 2. Now what do we do with the C value? You plug it back in, right? Put it right back in there. Okay, so T minus 100 natural log of 2 equals negative 100 natural log of absolute value of all that razzmatazz. There we go. All right, we got C. Oh, this is a problem that does not have K. Interesting. All right, we just had a C, didn't have a K. Now what do we do? Well, it says solve the differential equation. What does that mean? It means get the letter that was in the top right corner by itself. Didn't this start as a D capital T over D lowercase t? So just get capital T by itself and you're done. You solved the differential equation. All right. So, ooh, there's the capital T right there. Boy, it sure is embedded in a whole lot of stuff. We got to start undoing stuff to both sides to get it by itself. All right, let's see those equation solving skills from all those past classes you've taken. I want to get T by itself. I can't even really get into the absolute value yet because I'm kind of outside the house here. I've got to get rid of a negative 100 and I've got to get rid of a natural log so that I can get in the house and then save the T. All right, it's like a house fire. And so, first thing, the negative 100 is completely separate, if you will, times the natural log of everything else. The natural log is locked into this whole group down here. So between this group that has the capital T, which will protect, and this thing that's multiplying by it, of course you would get rid of that negative 100 first. And the opposite of multiplication is division. And oh, let's do this. Let's not put the whole thing over negative 100. This is a nice little trick here. Put each thing over negative 100 because we're going to get a nice little cross cancellation here. If you put it all over negative 100, you can't partially cross cancel and ignore the T. But if you separate your fractions, you can. Okay? That's a good strategy. All right. So now you've got, I don't like the negative on the bottom. Let me put that upstairs with the T. Negative T over 100. Minus cancels, and you get a plus, and then the 100s also cancel, and you get natural log 2. Not bad. Looking pretty nice over there. Over here, the negative 100s cancel, and you get natural log of absolute value of all that razzmatazz. Okay, you're one step closer. Then you go back to your integrated classes, and you say, boy, how do we used to get rid of natural log? Oh yeah, E. If you put an E on the right side, you put an E on the left side, but do not share the E's. You can't put an E. You're only allowed one E per side. And I'll see students try to sneak in a couple of E's right here. Only one E per side in this step right here. It's kind of E to the quantity. All that is what it really is. Okay? So be careful. Cancel. And now you've got absolute value of all that razzmatazz. And you're getting close now. Okay? You've got to be really good at solving equations in calculus. But this is going to make you strong. It'll make you stronger. Now this right here, oh, I know it's so tempting. I know you all want to cancel the E with the natural log right there, but you can't jump across addition or subtraction. Even if it was multiplication, you really couldn't cancel E with that and ignore that. Okay? E and natural log are very picky. It's got to be just E to the natural log of a single entity without anything else in front of the natural log. Okay. So you can't jump across there and do that. But wait a minute. But hold on a second. Way back in middle school, didn't you learn that x squared times x to the fifth was x to the 2 plus 5, which makes 7? So if you're adding exponents, Can't you go in reverse for the first time in your life and break it into same base to those individual powers? Okay. You see how we've got e to the all this stuff right here? You see how there's addition going on? If the powers are being added, the only way that could happen is if you came from two base e's that were each going to each one of these pieces, okay? It is literally exactly backwards from 7th grade, from this right here, okay? Addition of powers. Now you can break it into separate e's, but notice it's multiplication. It's certainly not addition. You certainly could not throw e's in there and put a plus sign. No. You'd have to do this first, then you have to do this, change it into a multiplication problem. It's so clever too. Calculus students love that every year, by the way. When I do this little thing, they're like, wow, that's pretty cool. And now you can cancel e and natural log. Now they're side by side, and 2 becomes the coefficient. Okay? 2e to the negative t over 100 equals all this stuff. Now, what's the next thing you have to do? You got to get in the house before you can save t, all right? We unlocked the front door. Somebody locked the front door and set the building on fire. My goodness. So the natural log, we unlocked it with an e. Now, we still have some barriers here. I guess you've got to open the door to actually get in it. You can't just unlock the door. You got to open the door. How do you get rid of bars? You simply drop the absolute value bars and toss a plus or minus on the other side. We've seen that in this chapter. Drop the bars, put a plus or minus over there. Now you are extremely close. Now, how many times has Mr. Wade preached this right here? The thing I'm trying to solve for, capital T, I don't want it to be negative. I like to keep my t's positive. Add, do not subtract 2 from both sides. Don't be an amateur. Add this negative thing over here, positive 0.01t, and because you're a super duper calculus student, subtract this one simultaneously back from the other side where the 2 is. Okay? Do 2 steps in 1. You're too smart to waste time on 2 separate steps here. Okay? So add the t over. Good, we got it to be positive. Then subtract this over from the 2. So let's put the 2 first, and I've got a new trick for you. When you subtract plus or minus something, we've never done that before. When you subtract it, doesn't it change to opposite? So the plus changes to minus, and the minus changes to plus. Now you have minus plus. Guess what? That's the same thing as plus minus. There's no such thing. We don't say minus plus in math. It's still plus or minus. So when you subtract a plus or minus, it just stays plus or minus. I mean, plus or minus is giving you both possibilities anyway, so it's still going to give you both possibilities. All right? I'll make some space in here. E to the negative, to the negative t over 100. Yeah, make sure I put the correct term here. Okay? So when you subtract a plus or minus, it's still plus or minus. When you add a plus or minus, it's still plus or minus. How about that? So now you're close, all right? Really working on our equation solving skills here. 1 step away, okay? Divide both sides by 0.01. You finally saved t. Wait a minute. Hold on a second. I don't like to put something over a decimal. You can't have a decimal in a fraction. There's something better we should be doing here. Isn't 0.01 the same as 1/100th? The very same 1/100th we started the problem with, actually. Okay? I would rather consider this not 0.01, but 1/100th. So you can mark that out and change it to this. It's really 1/100th coming back again like it did in the beginning. Multiply both sides by the reciprocal, 100 over 1. Okay? This is much better. Times 100. Cross cancels. Make sure that you do the 2 times 100 and also this other 2 times 100. It's a distributive property. So capital, boy, I'm out of room. Let's magically make this board erase over here. Abracadabra. Capital T equals 2 times 100 is 200 plus or minus 2 times 100 is also 200 e
to the negative t over 100 power. That looks so nice. All right? The real life temperature. Now, what was the derivative? The derivative was the temperature changing as the rolls are in the oven. The original capital T is simply just the temperature. Does that make sense? Derivative, how fast is the temperature changing? Original function, what's the temperature? Just how much is it? What's the amount? Okay? So now you're calculating temperature at each moment as the rolls warm up to the oven temperature. Interesting, okay? We did mention the other day, oh, remember, you can't leave a plus or minus in an equation. You can leave plus or minus constant in calculus. You can't leave plus or minus variable. You got to do one more thing. Figure out, is it the plus case or is it the minus case? There's one hint we had way back when we started this problem. Wasn't it lowercase t equals 0, capital T equals 0? Plug in a 0 for capital T. Leave that blank for a second. 200 plus or minus 200 e to the 0 over 100 is 0. What do I put in the middle? Not just equals. Does it equal? Remember our new game? All right, it's our new favorite game called Does It Equal? I don't know. 0, does it equal 200 plus or minus 200 e to the 0? When you end up with a plus or minus in differential equations, you need to go back and plug in either hint that you have if you have two hints. This time we only had one hint. Plug in the hint, figure out which case it is. It's going to be very obvious. 0, does it equal 200 plus or minus e to the 0 is 1. 1 times 200 is 200. Now, is 0 equal to 200 plus or minus 200? No. That's why if you don't put the question mark, they will kill you in college. The professor will take off points. You just stated that 0 equals 200 plus 200 or minus 200. I don't think so. This is two different numbers. That's one number. No. That's why you have to say, I don't know which one it is. And now it's very obvious. 200 plus 200 is not 0. 200 minus 200 is 0. It must be the minus that really worked with our original hint. So your final answer is to change that to a minus, and you can now find the temperature of the Sister Schubert sausage wrap rolls at any single time in the experiment. Now that is real life calculus and mighty tasty. I'm gonna go eat some rolls. Do the sample test.
Hold it now.
The real life temperature of the Sister Schubert sausage wrap roll of the Sister Schubert sausage of the Sister Schubert. This is a tongue twister. Why did I pick this? Of the Sister Schubert sausage wrap. The real life temperature of the Sister Schubert